Hey everybody, it's time for a little bit of office hours here. I'm gonna see if I get one thing printed up. Are we still playing Kahoot music in the background? I think we are. But if you are here, feel free to say hi. Okay, let's get the chats up. It's been a crazy week. If you had a crazy week, put it in the chat that you've had a crazy week. Crazy week. Crazy week. Nobody watching probably yet. Live chat, top chat, all the chats. Stranger Things season 5. Oh my gosh. Coming up here soon. I know they're going to do some craziness because it's the last season. So I'm going to try to not watch any previews for that and only watch it to see what's happening. Okay. I think we got things good to go. Office hours. Opening up the chat. We can start to do a little bit of the work right here. Do some My Pearson. That's always fun. Doing My Pearson. Maybe do the full homework. Maybe I'll send an announcement. I'll say we're going to do the full homework from today's lecture. Come in, get it done. Let's do that. Let's get some people in here. Let's see how many we can get. I'm going to give myself points for how many students I get in here. Okay. Because I know it's like 2 days after the test. Everyone's like, oh, gotta get some time off. Confidence intervals for the sample proportion. Okay. Oh, it's a big homework. Okay. So let's say currently doing a full homework. Okay, so announcements. Currently completing chapter 14, 13, or confidence interval, homework, help. Okay. Join in. I am about to do the full homework. Join in and complete it. See you there. Just click here. Okay. There we go. Good to go. Let's go over to the Discord. Yay, Briley and others. At Statool1. Okay. About to do the full homework from today's lecture. Join in. Okay. There we go. We got it. Okay. We'll see if we get some people in the chat. Let's go do the homework. So warm today in the office. I think they turned on the heat. Woo! The heat is on. It's in my room. Okay. First question here at 4:03. Stat 201. Chapter 13. Homework. And this is question 1. Okay, Pew Research took a random sample of 1,058 teens. 45% reported that they were online pretty much all the time. 95% confidence interval goes from 42 to 48%. Now, one thing we always like to say when doing these is to mark your notation. If you're in the chat, feel free to say hi. Hope we got a few people in here. Does it show? It might just be me watching still. But make sure to mark your notation. You should know what this all relates to right here. Notation is going to be so important for later in the semester. You bought it in the chat. So this right here is going to be the proportion from the sample. This is the sample size because it's not a population. They're saying they sampled this many, so that's a sample proportion over there. And then this is the lower bound on the interval, and this is the upper bound. And notice that p hat is technically 0.45 as that. So if p hat is equal to this, q hat is equal to this. Every question, mark the notation. I can't state that enough.
Notation, brother.
Mark your notation. I think there's even a test question. Well, I was teaching the test moments. I think there's even a test question that says, like, what is p hat or what is sample proportion? Might be on the last test too, but there are questions that literally just ask you like a notation thing, just a little quick quiz to see if you know it. So let's take a look at what they want us to do in this question, because I just kind of answered myself. Interpret this interval. Now, this is where MuBot's going to help you out. We covered this today in class 2 on how to interpret intervals. They might change up the wording a little bit, but I always like to say, I am blank % confident that the true blank is contained in the interval blank to blank. They might do 95% confident, depends on what interval they make, and then you do the lower to the upper here. We also have for other test 3 interpretations. So test 3 has interpretations that you'll either have to write out or fill in the blank. We might be changing it up a little bit this semester. So you always state your confidence first on how confident you are. Once again, don't read their answers. I am 90. What's up, Brock? Let's get this homework done. I am 95% confident that the true proportion of teenagers who are online all day the time is contained in the interval 42 to 48%. So it's not about the teens polled. That's wrong. It's not that there's a chance. It's if we asked all the teens. I am 95% confident that the true proportion of teens for everybody who are online all the time is contained in the interval that. There we go. They changed up a little bit. And what does 95% mean? We talked about this some in class, that if you were to repeatedly make these intervals, 95% of the time the truth would be contained in these intervals. So 95% of 95% confidence intervals contain the truth. We went into this a bit during lecture, how an interval doesn't contain the truth all the time. The percent confident means if you repeatedly use the interval, what percent of the time the interval would contain the truth. And it's kind of for like all 95% confidence intervals. 95% confidence intervals contain the truth 95% of the time. So there's a 5% of the time the intervals don't contain the truth, because sometimes the intervals don't contain the truth. Depends on the confidence interval. If one were to collect many samples of teens of this size, about 95% of the intervals would contain the truth. The sample size here is not super duper relevant. You do need to include it. But if you were to collect samples of size 1058 and make intervals from that, 95% of the 95% confidence intervals would contain the truth. That's what 95% confidence interval means. It doesn't mean there's 95% probability that the one interval contains it. It's a law of large numbers idea that over repeated trials of the interval. Brock, did you get that first one right? Are you already done with the first question on the assignment? So hopefully, Brock, first question done, and heading right into question 2. If I need to slow down, let me know. But there's some easier ones. Reaching out 2 standard errors makes us what % confident? Great job, Brock. And so we don't want to click the answer here. We want to know it before clicking it. Reaching out 2 standard errors, we talked about this today, makes us what % confident? About 2. It should say 1.96 technically. But reaching out about 2 standard errors. So if you reach out 2 standard errors. So a standard error is this right here. This is one standard error is this length, and that's another standard error. And standard errors are basically standard deviations. The formula has been changed slightly to include the p hat versus the standard deviation formula was p times q over n square root. So now that we put the hats over it, it's called a standard error. So what % confidence would this be, Brock? If you reach out about 2, technically 1.96. So think about your rule that you know. So what would this be? Take a guess if you want. I'll throw you points anyways for being here, but take a guess. You got it, and more points in the chat. That's a 95% confidence. More exactly, it's technically a z-score of 1.96. And that's the exact, but it's very close to 2. So about 95. There we go. That's got it. It's the empirical rule. There we go. If you know how to do a lot of these, it's very quick. A lot of these questions are like, oh, I know how to do that. Like this one right here, we need to find the margin of error. So while I'm typing in the notes right here, what is Brian's first suggestion for any question where you have to solve stuff? What is Brian's first suggestion for any question where you got to solve stuff? If you have to solve things, what do you need to do first? Notation, brother.
Notation, brother.
Notation, brother. So let's mark our notation. We got to find our pen first. Notation is going to be, we got the % who think we're going on the right direction, so that's p hat. The % who think we're going on the wrong direction, that's q hat, which is the proportion in the population conforming to whatever we're talking about. And we do write these as a decimal. When you multiply, you want to make sure they're decimals like 0.751, and q hat equals 0.249. The sample size is going to be, that's weird, it looks like a year, but that's the sample size. It was done in 2020. I think they updated these a while back because it had like 2005 when I first started these. So now it wants the margin of error. And it says 99% confidence. Now, 99% confidence relates to the z-score. some common z-scores are going to be, and I'm going to write these down for you. Actually, it'd probably be easier if I put it on a piece of paper. These are z-scores for your reference. So these are z-scores for you to use as a reference. So let's go to table, insert table, and let's go right here. The most common z-scores are very common ones. I'll show you how to get all of them. Okay, 68 you know is 1. And then let's go to 80. That's 1.2816. I'm only gonna do 2 decimals. There are more decimals, and we'll show how to get those. 90% is 1.645. Everyone does that one as 645 because everyone puts that as 1.645. 95% is very close to 2, but it's technically 1.96 or 1.5996 if you're very crazy like me. 98 is going to be 2.33, 2.3263. 99% is going to be 2.5758, so it rounds to 2.58 when it's rounded to 2 decimals. So what do you notice as we get more confident, the z-score gets what? Yeah, are these corresponding with each other? Correct. Like a 68% confidence interval is a z-score of about 1. They get bigger. And we can see this if we go to the applet, because what we're doing is we're covering more of the curve. So as we cover more area on the curve around the center, then we see a bigger z-score. So the applet is in the chat right now, and you have to click between, just like we did on our drawing. So remember on our drawing we did the middle area? You click between, and you can check my numbers. With 68, there's the exact, like I said, it's very close to 1. 68.26 is 1, but even there's more decimals after that. But 68% is basically a z-score of 1, and we'll do to 2 decimals. And then 95 is 1.96. 90, like we said, is 1.645. Oh, it's 1.6449. That's why it doesn't round up. So, yeah. A lot of people call 1.645. So usually people carry that last one right there. And then we said like 80 is 1.2816. If you go to the... No, 1.2812. Oh, it is 16. I gotta practice these again. And 99 is 2.33 if you round, but 2.3263. Oh, 99. 2.5758. I did 98. There you go. You don't have to memorize them. So, Brock, do you get what I'm saying right here? Do you have to memorize these? Yes or no? Do you have to memorize these? Yes or no for the test? Yes or no, you got to memorize these. Do you have to memorize these? No! And also, I made a nice little table with a lot of the values on them for you here. So these are the most common ones. You're probably not going to see any outside of that. These for the test. Or not for the test. We'll give them to you on the test. But on your homework assignments, you're not really going to see values outside of that. So this is very important because we have to calculate the margin of error, and the z-score for a 99% confidence interval, from what I just explained, is 2.58. Sure, I'll do the rounded version. I like doing 5758. It's a neat number. And then we figure out the margin of error. P hat plus or minus z star, which means you get to pick it, p hat q hat over n square root. Now, the reason this has a star is it's relative to how confident you are, and we are 99% confident, so it has to be 2.58 right there. But, Brock, real quick question. What of this formula is the margin of error? So what inside this formula here is the margin of error? It's everything after the where. Like everything after the z, everything after the p. Where's the margin of error? It's a very good thing to know about formulas because we'll see other formulas that have a margin of error. So where is the margin of error in this formula? It's everything where? Close. Very close, Brock. Good guess. Margin of error is a plus or minus. So the margin of error is this. It's everything after the plus or minus because it said plus or minus this. So the plus or minus, because like plus or minus is a margin of error. So it's everything after the plus or minus. Brock, really good try right there. I like it. So this is the margin of error, which is everything after the plus or minus. So all we do is we plug in, so z-score times the square root of p hat q hat over n. So we just plug in the numbers. We plug in 0.751 times 0.249 over 9, really. I ran out of room. Ay. One sec. You can't go but so low on the screen. 0.751 times 0.249 square. Oh, I didn't put the z. 2.58 times this quantity. There we go. Does that make sense? Can you understand this? This is the z-score. That's the p hat, q hat. P hat, q hat times z over n, square root. Please tell me if you can't read it. Okay. Wish I could have wrote it down there. 0.751 times 0.249 divided by 1997. Yeah, exactly. Just plug it in. And then times by 2.58. I wrote, 0.025. Round to 3 decimals. There we go. That's it. That's all we got to do. You just plug it in from the notation. If you know the notation, you can solve it. Explain what the margin of error means. It means the truth is probably within so many margin of errors. If we go 99, it would be like 3. Oh, it is 99% confident. So 2.58 technically. One is 99% confident that the true. So it says the observed. Oh, the way they phrase this one. That's such a weird. I'm pretty sure that's right. I do not like the way they phrase this. I wish they just said interpret the interval. I am 99% confident that the true proportion of adults who think we are on the right track, or whichever one you want, the wrong track in America, is contained in the interval. If you do 75 minus 2.5, 72.5 to 77.5, because it's plus or minus that. Does that make sense, Brock? That this interval would now, I'm going to call it 75, but the interval is going to be 75.1 technically, plus or minus 2.5%. So the interval goes as low as 72.6 and all the way up to 77.6. Yes, it does. Because the interval should have a length of 5, because 2 times the margin of error is the length of the interval. How's that sound right there, Brock? So we'd say I am 99% confident that the true proportion of adults who think we're on the wrong track is contained in the interval 72.6 to 77.6. Well, that's got it. One more question down. Okay. Make a 90% interval. Brock, tell me what to do, man. And then we're going to do it. That was a longer question, but we got this one. What are we going to do with this question? We're stuck, right? Until we do what? Questions get a lot easier if you get that notation, brother. You got it, Brock, right there. Do you see any notation as I start to fill this out, Brock? Do you see any notation on this screen? It says build a 90% confidence interval. So when it says build 90%, that's a z-score of 1.645. You can use the applets on the test. We'd give that to you. Nice job on the z, on the n. Yep, that is, I was literally looking at this and I thought z. That's a z of 1.645. You would go to the applet, which I'll put the app on the screen here again. You'd go to the applet to get this by going to the applet. Make sure you've selected between, find x using p-value, and put in 90, and then you get 1.645. Also, you can use my handy-dandy table I created with values that are very common, like 1.645 being for 90%. So the more confident you are, the bigger the z-score. So just understand where these values come from, and also we will give them to you on a test. So now we see the government found this right here. Woo. Oh, wait, Brock, one issue. Don't worry, though. That's the year. The sample size is over here, and this would then be p hat. And p hat as a proportion is going to be p hat 0.517 and q hat 0.0483. So that's, just make sure. So they give a lot of numbers sometimes. The year is, Rock knows, not Brock, but Rock knows. Year doesn't really matter in this one. So we solved the problem. How do we solve the problem? I know, right? I do that all the time. I've done it. You should look through my videos on this. I've gotten these wrong because I'll grab a wrong number. So, and then a lot of these, I want to tell you this. A lot of these steps I do about mark your notation is to help teach it, but also so I don't make mistakes, because I've made a few mistakes here and there. And so now we just write our formula. A p hat plus or minus z star times the square root of p hat times q hat over n. And that whole formula right there is going to equal to 0.517 plus or minus 1.645, and then square root, and then 4527.517 times 0.483. There we go. And these are the numbers. That's p hat and q hat. If you remember, that's 0.517, which is p hat, and 0.438, which is found by 1 minus p hat equals q hat, which is 1 minus 0.517. So that's how you get this value of q hat. They should add up to 1. If you've done this properly, p hat and q hat add up to 1. Okay. So let's plug the numbers in and let's get it. 0.517 times 0.483 divided by 4527 and square root. And this is the standard error right now. We've just solved for the standard error. Once we multiply it, it becomes the margin of error. And so the margin of error is about 1.2%. And we can memorize that because if we know the margin of error is 1.2%, then it's 0.517 plus or minus 1.2%, which brings us all the way down to 0.505. Oh, no, that's all right. And 0.529. So that is the lower and the upper bound. That's the lower and the upper bound. So that's good right there. 50.5 to 52.9. 50.5 to 52.9. There we go. 50.5 to 52.9. We should do it. 90% confident. I am 90% confident that the true, whatever we're trying to understand, the true proportion of people in California considering moving out of state is contained in the interval blank to blank. Not that I randomly sample. Yay, Maddie. Maddie, thank you for being here. I am. It says 1 is, but I like to say I am 90% confident that the true proportion of Californians considering moving out of state is contained in the interval 50.5 to 52.9. That's got it. Boop. So since the confidence interval, okay, so since high costs have been cited as a reason, if it can be reasonably considered sure that more than 50%, which we do have, our interval is completely above 50%, so the interval is greater than 50%, Californians, suppose the state government will consider investing in new affordable housing if this is the case, so they should consider it. Because we have evidence it's more than 50% are considering moving out of state. I'll just say this. I talked to my cousin in California. Man, homes in Knoxville would be like 3 to 4 times the value. I mean, we can't just move a home to California. But if you have like, 3,000 square foot home in Knoxville, maybe it's like 600,000-700,000 or something. It's gonna be like 2-3 million in California. Like that's what he was saying. He was like, my gosh. He's like, how much are homes in Knoxville? And I was like this. He's like, holy moly, it's expensive out here. He was saying. So man, I can't afford that. Crazy. Yeah. I don't know. I don't think he's moving. He loves it out there. He loves it. My cousin. Yeah, and there's a lot. Oh, yeah, we don't have state income tax here in Tennessee. So I think the last few states like Texas didn't have state income tax. Tennessee doesn't have state income tax. And so it's very interesting. It's civics class. We're talking about civics here. But those are the facts. Tennessee. So which of these statements correctly interprets a 95% confidence interval? I am 95% confident the true proportion of whatever we're talking about. And it's not always true proportion. I am 95% confident the true mean. I am 95% confident the true difference in the means. What is a 95% confidence interval trying to do? Well, I guess they're talking about proportions here, which I don't love. 95% of the sample is in the confidence interval. That is false. The confidence interval is trying to estimate the truth. 95% of the time, the sample proportion will be in the interval. That's false. Actually, 100% of the time, the sample proportion is there. The sample proportion is actually the center of the interval. If you look right here, this is the sample proportion denoted right there, and it's the center of the interval. So it's always going to be in the interval. Like it's the center of the interval. It's what creates the interval around the margin of error. So 100% of the time, the sample proportion is in the interval. So it has to be this one. 95% of samples will produce a confidence interval that contains the truth. I wish that just said the truth. So it'd be more general right there, but 95% of confidence intervals contain the truth. Whatever we're trying to figure out the truth of, true proportion, true mean, true standard deviation, true whatever. Well, that was an easy one. Brock and Maddie, are we halfway done with this assignment? 55s. I mean, be like, I'm done with the work. Here we go. I want to make sure you understand it too. That's why I like pause on one of those. So this one has, nice job, Brock. This one has conditions. You ready? Don't even look at their conditions. That's all right, Maddie. Let's do this one. Let's get this one done. You ready? So hey, jump to this one with us right now. Don't worry, you can jump around the homework, and I'll have these marked in here so you can come back. But all the questions are marked, so you can check out timestamps here to see which ones we're doing and when. But jump to question number 6 with us, and let's do it. Condition 1. What's condition 1? Remember, we're learning how to memorize these. What's condition 1? I'll give you a hint. What's condition 1? Random. Did we randomly take these observations? What's conditions 2? Because we're talking to people in California. You about love some randomness. What's condition 2? Condition 2 is 10%, meaning less than 10% of the population is sampled. Do you think yes or no? Is this less than 10% of the population? We talked to 4,527 Californians. Do you think that's less than 10% of California? Because you look at sample size, yeah, it's way less. In California's like millions or something, or trillions. Not really. What's the last condition? So it's random, 10%, and then we usually pause. And the last condition here depends on the type of the data. We're working with categorical data. So the last condition is what? Don't even look at their answers. You got to know how to do it for the test. Success, failure. You got it, Maddie. You're right. It's success, failure because it's categorical. And we would check this via NP hat and Q hat. So we can do NP hat and Q hat to see if we have enough successes, enough failures. And so this right here, this is going to be P hat, and this is going to be N. So if P hat is equal to 0.522, Q hat is equal to 0.478, because P hat or Q hat is 1 minus P hat. So Q hat is equal to 1 minus P hat. So that's it right there. And really, if you think about it logically, which is all right, you can just think about it. You can just say, well, 47% of that is more than 10, because we have to do NP hat greater than and NQ hat greater than 10. And you only have to do the smaller one, because if the smaller one's bigger, the other one's bigger too. So you just go here, and you check the condition. So you go 0.478, 47.8% times the 4527, and there it is. It's 2,000, so we're good to go. So there you go. We didn't even have to read all that. There we go. It says right here, the margin of error of all Californians when measured on a 95% confidence is this. Would it be bigger or smaller if you're 85% confident? If I'm saying 68% confident and then I go to 95, what's going to happen to my hands? You know when I do the 68, 95, 99.7? So don't worry about their question yet. But if I say 95, what should I do with my hands? Should I do this? I'm saying 68. Do I go like this? 68, 95, further apart. Okay? So it says now we're going, it says, would the margin of error be larger or smaller for 85? So if you're at 95, what should I do with my hands? We're at 95 right now, it says. The question says we're at 95. I think I wasn't blocking it. What do I do if it goes 85? Smaller, less confident, right? Tighter interval. So to be less confident, which it is, the interval would contain the truth less, and it'd be smaller. So you would contain the truth less because you'd make a smaller interval. And we can see this here visually when you go from a 95%, it's a wider interval, to an 85, it's a smaller interval. So 95, 85. 90, wait, that was not 85. 95, 85. 95, 85. 95, 85. Or I can just do this now. There, oh. 95, 85. 95, 85. It shows 50% for a second, which is way smaller too. But yeah, just trying to show you visually. But that was it. That was easy. 85% confidence intervals are less confident than a 95% confidence interval because they contain the truth less and they're less confident. Okay. This one gets a lot of people. This is one of my favorite ones. I have a lot of favorite questions. Okay, let's do it. Okay. Several factors are part of creating an interval. For a given sample size, higher confidence means a smaller margin of error. Okay. So what in this formula control is related to confidence? This is a good quiz type question. In this formula I'm writing, which metric relates to how confident we are? Which metric in this formula relates to how confident we are? Which one of these is specifically, is it p hat, is it q hat, is it n, is it z? Which of these is specifically related to how confident we are? Which of those, just take a guess, don't worry if you're wrong. You're more likely to remember if you guess, and they're like, oh, it was this. Well, p hat relates to the sample proportion. So p hat, good guess, Brock, is sample proportion. So it doesn't deal with how confident we are. It is the z-score, because that's actually what we're getting from the normal curve applet. We're getting the z-score. So if you notice, there it is right there. So when you get more confident, the z-score gets bigger. So that's how confident we are. And the z-score gets bigger the more confident we are. Great job, Maddie, right there. And Brock, too. So, whoops, went to the wrong screen. So higher confidence would mean z-score is getting bigger. Like higher confidence relates to this going up. So if z gets bigger, what happens to the margin of error? The margin of, if z gets bigger, like if you make z bigger, what happens to the margin of error? If z were to be a bigger number, like you plug into the z like 5, 10, 15, 20, what happens to margin of error? You would never plug in like 20. That's huge z-score. But if you were to plug in bigger numbers to z, the margin of error would do what? Which is what I highlighted here in green. What happens to it? What happens mathematically? It gets bigger. Yeah, just mathematically. It's just you plug in a number there, it gets bigger. So this statement is false. It does not get smaller. It gets bigger. So this is a false statement because remember when we say like 68, 95, 99.7, we're moving our hands further apart. So you can even do it that way when you think about it without looking at the formula, that higher confidence makes for bigger intervals. Like all else the same, higher confidence means larger intervals. Be very careful they move the true and the false. Larger samples provide smaller margins of error. So we can look at the formula here again. I need to screenshot it. What does a larger sample mean? What is bigger? Larger samples provide smaller margins of error. So what does that relate to in this formula? N. So larger sample, that means this goes up. Margin of error, it's once again this. So it's saying it provides smaller margin. Will this go down? Because you're dividing by n. So if n gets to be a bigger number, is it true that this whole thing that you're multiplying gets smaller? Is it true? Is that a fact? Exactly. Because you're dividing by bigger numbers. Yeah. If you make this bigger, so larger samples, and think about that. If you take a really big sample, then your uncertainty margin of error, because that's margin of error is like uncertainty. Your uncertainty is going to be smaller with a bigger sample. So this is very, very true right here. If you take bigger samples, you will have less uncertainty. So this is extremely true. For a fixed margin of error, this question is wacky. This one's tough. Like the understanding of it. When it says a fixed margin of error, what it means mathematically is that, let's say margin of error equals 2. So margin of error has to solve to 2. I want it blue. Margin of error has to equal 2. And that means, and we're just pretending, that when we solve out z times p hat, q hat over n, it has to equal 2. Like for fixed. That's what the idea of fixed means. This number can't change. So you have a fixed margin of error. Larger samples. So a larger sample relates to n is bigger. So if n is bigger, that'll make this get smaller. And then what we'd have to do to counterbalance that is we'd have to put greater confidence, and that would make this get bigger. Because the n is inversely related because you're dividing by n. So these two right here, as the orange goes up, it makes this bigger. But as the sample size goes up, it makes it smaller. They like cancel each other out, or you can use them to cancel each other out. Like if you increase n, you could keep this the same by increasing z. Who follows me on this logic? Like this right here is inversely related to this value because you're dividing by, and this is positively related to it because you're timesing by. So they counterbalance. Yeah. So it's very true because they will cancel. Like larger samples provide greater confidence. The Z is related to the confidence. And so that's very true. Knowing the formula is the key for these. For a given confidence level, having the margin of error requires twice the sample size. The answer is no. It requires 4 times, and I can show that mathematically. And let me not hit next question. So it requires 4 times technically for a given confidence interval if you have the margin of error. So the margin of error is everything after the plus or minus. It's Z times P hat times Q hat over N. And if you want to see what happens here, if you want to times by 1/2, how does this impact N? Can I just put the 2 right here? Is that the way they combined? Maddie, yes or no? Is that you just take the 2 and when you multiply them, you just put the 2 right in there? Can I just do that? Is that how you multiply? Because I'm saying, like, let's cut the margin. No, you can't just do that. What you have to do is you have to re-express it. And you can re-express this as 1 over or square root of 1/4. If you don't believe me, square root of 1/4 is just 1/2. So if you go here to 1/4, which is that, and you square root it, you get a half. It's also, you think about this, square root of 4. If you want to rewrite this, you could do square root of 1. Yeah, I know, right? And then this can now go inside of here, and you can do this. So it actually requires 4 times the sample size. So that's, I don't think it appears anywhere on the test, but you can re-express it. Is it just 4? Yeah, it's not on the test. It's not a teaching the test moment. It's not one. It's just a fun fact. If you want 1/3 of it, you have to take 9 times. If you want 1/4 of it, you have to take 16 times. It could become a test question eventually. Like the idea of like, to decrease the margin of error, it requires ever larger sample sizes. Like decreases to margin of error are not quick. They require like exponentially larger sample sizes. Your margin of error goes like this. It slows down on how much it decreases related to sample size. Like sample size has a diminishing return on how fast it decreases. It's not a good test. It's hard to quiz on. Okay. 2 more questions. I'm more concerned about the other ones and you knowing the formula for that last one. The formula is what you really need to know. Last 2 questions. A student is considering publishing a magazine about Japanese automobiles. He wants to estimate the fraction of cars in the United States that are made in Japan. The computer output to the right summarizes the results. I am 95% confident the true proportion of cars, which you notice right here, that are made in Japan is contained in the interval 34% to 48%. We are 95% confident that between... Yeah, that sounds about right. Wow, it was easy. I am 95% confident the true proportion of cars made in Japan is contained in the interval blank to blank. I thought it was going to have more parts. I could have calculated the margin of error on that. Yeah, it's not just... just remember our interpretations. I am blank percent confident that the true whatever we're talking about is contained in the interval. A lot of people say true proportion because we learned it first, but remember it doesn't have to be true proportion. Okay. We got a store right here. They found that 14 of the 28 packages labeled red snapper were actually some other kind of fish. What? So what percent of the things in the store were some other kind of fish? 14 out of 18 were some other kind of fish. What percent in the store? So it doesn't ask us that, but once again, we're just learning how to do these. So what percent in the store were some other kind of fish? I'll start marking your notation for you. 50%. You're right, Brock. I'm so glad you said that. All people are like, how do I find that? It's just, what percent? It's like, sometimes we got our stats mind on and we don't realize, wait, I know how to do this. I've done it before. It's just what percent? It's a 14 out of 28. And that's technically P hat right there is 14 out of 28, which you know is so cool. What is Q hat? What is Q hat? If P hat is 0.50, what is Q hat? It's nice and easy. Because they add up to 1. There we go. That easy. So in this, the first thing we would want is we want these to be randomly bought, and they do say it is random, so that matches condition 1. This is a simple random sample. Next thing is these red snapper packages need to be less than 10% of all packaged fish out there labeled red snapper Do you think we pass condition 2 that these red snapper packages, we bought the 28 of them, is less than 10% of all packages labeled red snapper fishes? Red snappers fishes. Can't even speak. Do you think it's less than 10%? Yes or no? So to do this condition, the 10% condition, we ask ourselves, oh yeah, I think it is. Yeah. We bought 28 and how many total? Thousands, right? Like thousands. So it's thousands or tens of thousands of packages labeled red snapper fishes. So all we're asking is our sample less than 10% of the population? There's definitely more than like 1,000 packages labeled red snapper. I would say we have good evidence. What's the last condition to check? Condition 3, we pause. What is condition 3? We took a random sample that's less than 10% of the population. We need what? Success failure. Which actually the answer is this. This is actually n p hat. It's because if you look at how p hat is calculated, it's x over n. And so to calculate x, you could literally just multiply both sides by n, and it cancels out here, and x is n p hat. Does that make sense? Like, do you notice how the formula for p hat is equal to x over n? So that's right up there. And so you can literally just go times n, but these n's then cancel. And so np hat is actually x. You can confirm this too if you want, because you can just go here and say, we'd go np hat equals to 28 times 50% equals 14, and then the other one's 14 also, because nq hat is also 28 times 0.150. So do we pass the success failure condition, yes or no? Do we pass success failure? These are the numbers for success failure. Do we pass it? We took a random sample. It's less than 10% of the population. Do we pass success failure? Oh, yeah. Yeah, we pass. At least 10 successes, at least 10 failures. So we find the answer. There is at least 10 successes, at least 10 failures. That's got it. Construct a 95% confidence interval. Once again, the notation is going to be huge here. So all we have to do is start solving the notation. Our peel filling, and remember, this is 95%. So the way to get the z star for it, I hope people are feeling a little bit better. The formula is p hat plus or minus z star, p hat times q hat over n square root. And z can be found with the applet right here. And we can go to the amps and enter in 95 and get 1.96. Basically, you know what, Maddie? Let's try 2. I'd probably, if for all intents and purposes, it's basically 2, but it's technically 1.96. But basically 2. I mean, when I do it in my head, I do 2. Like, I'll try to do a quick solve of it. Here's my quick solve to see if I get it. P hat times q hat over n square root times 2. So that's a margin of error of 19%. So how many decimals? 3 decimals. It's going to be iffy, but and it wants it as a percent, right? Or there we go. This is me doing a quick solve in my head. We'll see if I get it. The answer is nope. And here's me carrying out the decimals on this. So it's going to have a 1 on it. Or wait. This will be 8, 9. This will be 1. It worked with 2. So, Maddie, it actually worked with 2, but the technical number is 1.96. Let me show the math on this, but it technically worked with 2. It's close enough. That's why we say it's basically 2. It's more accurately 1.96 as shown here. You can see the 95% confidence interval is a z-score of 1.96, but when you reduce it down, it's basically 2. Like, it's very much 2, but it's 1.95996. So, and then I made this table of very common values right here to show you 80%, 90, 95, 98, 99. Also the applet. But to solve the problem, to do it, I'm going to write my math out. We just solve the equation. So the equation is going to be 50%, that's p hat, plus or minus the z-score of 1.96, and then 0.5 times 0.5 over the square root, or over 28 square root. And this is equal to 0.5 times 0.5 divided by 28 square root times 1.96. And so, wow, it was pretty generous to us. So that's the margin of error. Margin of error is 0.185. So it's margin of error is 0.185. And then the center of it's 0.50. So this is the interval. And we'll do it in a different color here. This is the interval, which equates to you subtract and you get 0.315. And then you add to it and you get 0.685. And it was very nice. There it is. That's the interval. And once again, we got it. Okay, let's look at the last part here. Explain what this means. I am 95% confident that the true proportion of all red snappers, not the ones purchased for the study, but sold in food stores in America, and we'll just show that the other answer would work, 31.5 and 68.5. Probably there's a decent margin of error on the answers it gives, but I am 95% confident that the true proportion of all red snappers across the country that aren't red snappers contained in the interval 31.5 to 68.5. Yay! Brock, did you get the full thing done? I am 95% confident that the true proportion of red snapper packages that are not red snapper is contained in the interval 31.5 to 68.5. Nice job, Brock. It's like 30, 40 minutes. You got the full thing done. One homework done. Well, I got some stuff to print off. Maddie, do you have any questions? Any other questions? Thank you, everybody. I'm going to save it right here. The full homework is done. How many people we got watching? 3 people. 3 people watching. I'm loud. You're welcome, Brock. You're welcome. I get so many, Ooh. What was this email? Interactives. Oh. I get so many things from random. You're welcome, Maddie. I get so many random things. It's nonsense. Well, I'm going to head off, print some stuff off. Bye, everyone. Great job, Maddie. Great job, Brock. Great job, everyone else. Bye.